And
Hello,
we are
everyone. Yeah, we are
live.
live. Hello,
Hello.
everyone. Yeah, and welcome to the 71st episode of DevKami, and I am Chi Leung.
I'm Suming, and our
And
guest here is
Shawn.
uh,
Hi.
Sean. Sean, what?
we
Well,
didn't
this
focus.
comes much later. So
Yeah,
as usual, we have to cover our two things.
yeah, which is not
So let's
much
start
for the
with
day.
our meetups. So the only meetups until next week is actually the IO Foundation Assembly. It's actually started yesterday.
Do you know what is that about?
I don't know. Oh, actually, it's on the date. It's on during my day job, so I don't know the event.
Okay.
But this should happen. This should happen at. This should happen. I don't have the detail.
I'm gonna fill it up afterwards.
Yeah. So otherwise, we won't have event next week. Partly, I believe, which a lot of people are still worried about the virus.
Yeah,
So
and a lot of the time, the building management are definitely gonna be more reluctant in
yes,
letting people in.
nowadays, even my building actually have the thermal camera now.
It's not like for certain buildings, like corporate buildings, they to get in for meetups is already pretty much a lot of work to get people in. We have to get the ICP registered,
Yeah,
submit it to the security team. So
yeah,
I think for the virus outbreak, it's gonna be much more stricter.
yeah. So la la la. So I think that's about
No,
it lah. So what's for
yeah,
the news? We have a
uh,
few. We have a
yeah.
few, but we have a few. So
You,
let's see. Kubernetes is more expensive.
for the Google one, GKE is gonna be
Yes,
more expensive. They
correct.
charge a management fee. So if that is basically literally translate to $41 per month, around like
Yep.
that. So it's pretty much pretty expensive actually.
Then
So
Microsoft. Oh, so that's what to them on that. So will you guys be using GKE soon, or will be like
no,
stock for now,
no, I'm
or
not
don't actually
using
have a
GKE.
choice?
But if you use NSOS, I think they are pushing you towards that direction. NSOS is
Okay.
like a hybrid uh, cloud light. They basically you can have your own what do you call it? Your own infra, and you can still
On-premise.
leverage on premise. Yeah, forgot about it. And you can still leverage like the some of the API or the management console of Google. So for that, they don't charge you a fee. But
So
for
okay.
our case,
Yeah.
we actually don't use GKE that much.
Right. So our next thing is okay. Windows. There's a Windows Open SSH client. I thought that exists for a while, but apparently this is on GitHub now for PowerShell. That's a Windows. One of the shell on Windows. So I think that's the two news that I can find. Any other news you can find around?
Not so much.
Yeah. So it's the virus. Uh, I blame the virus.
If you want to consider that as news, is Microsoft is retiring its MCSA, MCSD, and
Oh yeah,
MCSC
that's important.
certification. Yeah,
Okay.
so they're
So
gonna
they will
move
focus
towards
on
role-based training. So like following the bandwagon of like Amazon or Google,
hmm,
like cloud architect kind of training, something like that,
right.
role-based. So
It used to be a joke among the open source community that we don't need bloody certification. We're proud hacker type.
yeah.
What
The
certification?
We
companies that
can
look at it.
we can talk about that with Shawn.
So that's it. I think we can end our
Yeah,
news there.
yep, that's about it.
So we have here is Sean. Sean is a electronic engineer and know about microprocessors and stuff. Nerd. I know he's pretty geeky and stuff. I think. Anything else you want to say about yourself, Sean?
Hi everyone. I'm Shawn. Um, I'm actually the principal engineer at ST, that's AESTE, and we do everything from chip design to software. So
Okay.
everything in the computing stack, basically.
All right.
I always try to tell people from silicon to software.
Cool. So, so here's a question I want to know. So when you said chip design, you really thought about designing microprocessors and all that, right?
Yes, chip design. Yes. So whatever the clients want us to design for them. Like a couple,
Okay.
like about the end of 2018, I actually had a client who actually asked me to help him to design a custom miner for a cryptocurrency.
Right.
Chips.
That's a matter.
Okay.
Custom chip for him to mine lah.
Okay.
That's yeah,
So what kind? Okay, so we're gonna talk about the industry a little. Chip design is from my knowledge, like is usually for the big company. You almost never get into it unless you're the Intel, the AMD. How does a small player can get in?
That is very true. But chip design is a whole spectrum. So what you're mentioning are what we call the custom chip or the semi-custom chip designs, which are the kind of things that people like Intel and all those kind of people do. That you need a lot of budget because even the software licensing can cost you millions.
Right.
I used to intern in one of these companies that do the software one. So it's how they sell corporate software, right? They sell you the basic package. You cannot do anything. They already cost millions. And then add on some more millions. So in the end, it's like tens of millions just to get like a single user license or 5 user license. Right? So those are the big boys. But for the small guys, then what we do is we can focus slightly differently. So smaller companies tend to do FPGA based designs. And again, we are more focused on the design part, so not so much on the manufacturing part, because a lot of the cost actually goes into the manufacturing side. If you want to talk to a cheap fab, unless you have like 8-9 figures in the bank, they won't even bother to pick up a phone call.
Okay.
So for small guys, that's what we do. We focus more towards like the FPGA side of things, and also doing
what
the design.
What is a FPGA? I mean, let's assume that people don't know.
All right. Yeah. So FPGA, if you look it up, it stands for Field Programmable Gate Array. So it's basically a chip, but it's a chip that the hardware is completely configurable. So the hardware itself is not fixed. The circuit itself is not fixed. So that is what we do. We design it and then we input the design into a FPGA. So that will basically wire up the hardware in a certain way to become certain circuits. So that's what FPGA is. Normally it's used mainly for prototyping, especially if you're going to go to a full custom chip. You usually start with the FPGA first for testing, right? But you can also actually use FPGA in a lot of end applications. And nowadays you actually find FPGAs all over the place. Sometimes you don't even realize it's there, but it's actually hidden somewhere inside.
Right. So what's the difference? Okay, so we keep hearing things like ASIC and FPGA together. What's the difference?
So FPGA is a programmable chip. So literally you can change the circuit. That's why it's called field programmable. You can literally change the circuit by just downloading a new image or new firmware. Right? So that basically changes the circuit. Whereas the ASIC, which stands for application specific integrated circuit, that is a fixed hardware circuit. So that one you cannot easily change. If you want to change, it costs you tens of millions or hundreds of millions of dollars and go through the whole cycle of design and test and manufacturing.
Right. So how do you actually program FPGA?
Basically, the process flow is fairly simple. So there's what we call a FPGA design flow, right? So what you start with design entry. The first stage is called design entry. There are many ways to do it, but you can literally draw schematic diagrams like circuit schematics if you want. But of course, most people don't do that. They do some sort of coding. Right? Typically, the most popular languages are Verilog and VHDL. So they use code. So it's kind of like programming, but you're using code to actually describe circuits. So we are not using code to describe program flow. We're using it to describe circuits. And then once you have done the design entry, right, then the next stage will typically be synthesis. which is a little bit like a software compilation. So it is a tool that basically is a process that actually takes the code that we've written in Verilog or HDL, and then it converts it into a circuit. Right. So then that circuit then goes through a bunch of other processes, place and route mapping and things like that, which will actually implement it in a real physical circuit. And then that one, at the end of the day, we get a file that we call a bitstream, and then that bitstream we download onto the FPGA. And then the FPGA will then form that circuit that we want.
Cool. So as you actually design circuit, do you guys okay? So, like most engineering, I will assume that you will have like pre-made blocks and all that to use, right? It's a module of software, so that exists. How about things like what kind of level we're talking about of the abstraction? Is it like a one memory? This block is we had a pre-built block for memories and all that, something like that.
Okay, so a typical FPGA comes with a set of primitives, but they are quite low level. All right, so you have the most basic primitive, you usually have something called like a flip-flop. A flip-flop, and then you have ability to do logic gates. So that's basically that's it. And then from there we can also run some of them of course have more canggih stuff, more advanced stuff. Right, but basically that's it. And then we can have things like multiplexers, or like you mentioned, we have RAM. We also have block. We have different types of RAM as well in the FPGA, not just a normal RAM. And then some FPGAs have different things like accelerators, like ability to do certain kind of, let's say, signal processing applications faster. So those hard blocks are also in there. But otherwise, generally speaking, there is not as much modularity in chip design than as compared to software. Because even the pre-made modules, they are usually very specific to, let's say, certain FPGAs or certain ASICs. Because if, let's say, for example, you need a 6-gate AND, and then this particular chip doesn't have a 6-gate AND, then you have to implement it in a different way, like 4-gate and 2-gate or something like that. Right? So there is a little bit less modularity. A lot of work is still very specific.
And I also can imagine that a lot of work is also a lot more low level. You can't even start with 1 plus 1. You literally need to implement an adder to before you can do 1 plus 1.
Actually, you can. All right. For in most cases, you are talking an example of adder in most cases, you can write a piece of code in Verilog. Let's say A equals to B plus C, right? And that plus, when you pass it through a synthesis tool, the synthesis tool will then infer an adder, and then you pop in a circuit for an adder for you.
Right. Okay. Interesting. So how about impact of things like architecture? So there is other architecture other than x86. So we have things like these. We have ARMs. How does that impact the design? Or it really doesn't matter in that case?
As far as, if you look at it from the perspective of electronics, it is either way also it's just a circuit. Right? So if somebody asks you to ask me to design a RISC processor, or if somebody asks me to design a CISC processor, either way also it can be done. It's just a choice that has to be made depending on what you want.
Okay. So when you design a processor, it's pretty much based on this architecture, or is this your own architecture? As in, will it be something that is totally different with a different instruction and all
that? If you're talking about the processors that I have designed before, right? I've designed like a number of processors. I've a talk on YouTube called the Tale of 5 microprocessors. Right. So, I designed a number of microprocessors, and basically they are essentially clones of existing processors in the sense of the instruction set. So all I do is I borrow the instruction set, so that I don't need to go and re-implement everything from the compiler, assembler and things like that. I can reuse existing software. But the actual physical architecture of the processor itself, I usually do it differently. So like, for example, the first processor I ever designed was a clone of the 68K. I call it the K68. It is the original 68K was a CISC processor, complex instruction set computing, CISC. But when I implemented it, I didn't implement it as a CISC processor. I changed it. to use a different architecture. And so architecture-wise is different, but the software-wise, I still use the original 68K compiler and assembler to actually write software and run.
Oh, okay. So in this case, I actually confused between architecture and instruction set. Yeah. Because
yes.
instruction set is essentially like analogy will be something like your car interface. Every car is the same, wheels and all that, but how you build the car is very different. Something along the way. Okay.
Instruction set are just the commands that you give, but the commands need to be interpreted and performed by a machine. So the architecture of the machine that actually interprets it, the architecture can be all kinds of architecture.
Right.
That's the part where I will implement things differently.
Right. So in your line of work, will it be just microprocessor? It could be something else actually.
Oh, can design anything because I'm a computer engineer / electronics engineer. So anything like say example was the client that actually asked us to design a cryptocurrency miner. Also can do.
Okay. All right. Okay, so some of the question that the engineers, by people, and everyone else keep asking is, what's the difference between a microprocessor and microcontroller?
Okay, the classical answer to give you will be a microprocessor is just a microprocessor, a CPU, right? And a microcontroller is basically a microprocessor plus I/O devices plus memory.
Right.
So all in one device.
Okay.
That's it.
How about the definition nowadays? Because nowadays the definition is getting weird. Because so for your PC, the microprocessor is really a microprocessor. It just maybe a GPU, right? But on the embedded system side, I refuse to call it IoT because that's a very dirty word for me. So on an embedded side, it's microcontroller, but sometimes those things are split out as well, right? I don't know.
There's a classical definition that would be it But today, like especially you pointed out clearly, things are getting very confused because the microcontroller / microprocessors are getting very weird. All kinds of some got multiple cores, some they have RAM inside, some the RAM is outside, but then they have I/O devices attached to it. Some they don't. They have everything together. All kinds of architectures are there. So today it's more blurred right? But if you ask me, most embedded systems these days it's still basically microcontroller based because usually we like to have things in a single chip. Everything on the same chip saves cost because one chip can do everything So rather than having multiple chips and all right? So in embedded systems, typically it will still be microcontrollers rather than microprocessors.
Right. So even though things like the ESP that usually have the whole Wi-Fi, it's crazy. Okay.
Now in fact we actually call those things SoCs. System on chips. Yeah. So it's because you really cram so many things inside already, right? It's like this guy can do everything already.
Okay.
It's basically one whole PC and one little chip So
right.
It's a whole system already. It's no longer just a microcontroller anymore.
So why don't we see more of those around? Or we already see it's called cell phone or something like that.
Actually, SoCs have been a trend for the last 20 years or so.
Right.
So actually, it's everywhere already. But
okay.
As you pointed out, you may not realize it only, but it's everywhere.
Right. So I'm going to drag a bit back to the software side, right? So let's say you have something that's compatible with a similar instruction set and all that. How do you actually integrate a compiler to it? When you have something that's compatible, does it mean that it's automatically able to run a Linux system on it, or you actually have to spend a lot more work before you can start?
That would usually depend on how close or how compatible is it, whether it's 100% exactly the same.
Right.
Like for example, in Intel or AMD processor, it's typically almost 100% compatible right? So your software doesn't even need to be changed, you drop it in and it'll run, right? But in the case of the processors that I have designed, usually the architecture is only about 99% compatible. I don't 100% compatible. So that it would still require certain changes. to the software. So either at the compiler or at the low-level library stage. Like for example, there was another processor that I cloned, the microblaze. The standard microblaze was single-threaded, but my one that I cloned, I put it multi-threaded in hardware. So the hardware is still running multiple threads. So as a result, if you just take the original software and you just dump it into my processor, you end up running 2 copies of the code at the same time. So in the end, what I had to do was basically to change the low-level libraries and change the boot up code, the what they call the C runtime, so that it actually splits things up into separate threads, and then after that, if you put an OS on it, and then the OS will then take care of those running different tasks on different threads and things like that. But you have to actually change certain things.
Right. So why is it then sometimes when we have sometimes as a hobbyist that we will get like various ARM-based development board and all that. It's actually very frustrating to actually import an OS. Often you can't get Android running, for example. What is the reason that it's mostly compatible?
Okay, if you pick the example of ARM, that's an awesome example to pick because there's no such thing as an ARM processor.
Right.
ARM is it's basically a family of processors, or a family of processor IPs only, not even the whole processor, just the core or the design of the core processor. And then that processor, those different manufacturers all take and then they add on different things to the main ARM processor to form their ARM SoCs. So that is the biggest problem you have, because in the end you end up with like tens of thousands or hundreds of thousands of variations of a processor, or rather the processor family. It's not even one processor. So if let's say you have an OS particularly ported to one particular hardware, you get another piece of ARM processor, even if it comes from the same generation, same family, but you may have a different set of peripherals around it, and that will totally throw it off. It cannot be directly ported, cannot directly plug or run the software in the new processor, because for example, even something as simple as the memory locations for things can be different. So the addresses for everything is different. So the software cannot just directly just run like that. You have to actually port it, and then it's usually what they call the board support package, BSP, which will include the variations what are available in there.
Right. And as a result, you don't simply run Linux on an ARM processor.
No, you run Linux on a very specific ARM device.
Right.
Right, and then if you have another device, if it so happen compatible, as in it's very same come from same manufacturer, same model, and things like that, then no, usually less problem. But if it's from completely different manufacturer, don't dream about just running things like that.
I have a question. Does it mean that ARM is actually just a family of instructions, common instruction instead of underneath chip design?
In a way, you can think about it that way, because ARM doesn't actually make any chips. ARM actually just does the design of the chip. And then ARM doesn't just do the processor either. They also sell a bunch of other I/O peripherals and stuff like that are attached to the processor. So, and then a licensee, when they actually want to license an ARM, they actually have to pay like for every little piece of thing that they want to add on. So they get one ARM core. ARM got so many cores, like let's say a Cortex M, Cortex A, Cortex R, even the M got so many, M0, M1, M2, M3, M4, M7, and on. So you have to pay license for which core you want, and then you have to pay license for the I/O stuff that you want, the bus that you want. Everything is pick and choose one. It's like going to a supermarket, pick what you want. Then you go to checkout, and then ARM will tell you, this is how much it costs to license it. Right? So every company that's an ARM licensee actually basically has different processors, because they mix and match different things. And then sometimes they even add on their own custom stuff. Like nowadays you see a lot of these phones, they have what they call a neural network processor, or AI processor, right? So that one is like custom stuff that they add on themselves. So it just completely makes things completely different. The only thing that is putting them all together is like you mentioned, they have the same instruction set, and they use like the same similar kind of software tools that come from the same source. And in that sense, ARM is doing a pretty good job, because they actually control these things quite well. They don't just let people do whatever they want. Everything needs to basically fall back to the ARM way of doing things. There's a prescribed way of doing things. If you don't follow, of course you can want to follow, but when you don't follow, then you have to, makan yourself lah, cak kaki lah.
Okay.
You have to take care of things yourself. So usually people will follow lah.
Okay. Let's talk. Okay, so there's actually I can't think of anything about architecture now, so I'm going to move forward. The reason why I bring you in, one reason I bring you in is because I know you for a while, so we talk hardware for a while. But one thing that reminds me to bring you to interview is actually that you had a series of interesting processes. So interesting processes cover things like the 68K. That's what the earliest bag is running. The early 86 x86 and all that. So let's bring up high level why you start with this.
Well,
this project.
It's something that I'm personally passionate about. I like processors.
Right. Okay.
So then I thought it's a good opportunity to share some of my knowledge. Since I've spent a lot of time studying processors, I know quite a bit about processors. So I thought maybe something I can share and, like I said, educate and entertain if it's entertaining
Okay.
Right? But that's basically it. And I also have a collection of processors actually with me. Some at home, some in my company. Physical processors. Right. So I thought that something I can talk about.
Okay. So there's two levels of it. So let's start with the layperson. As a layperson, what should we know about microprocessors and what's interesting about it, and then go down one level. As a software developer, especially, what should we know about microprocessor, and what's the interesting thing that we should really know about?
What do you mean by know about? From what perspective?
What is the most interesting that
you want to buy one?
Know about? So.
Okay. All right. There are many things to know about microprocessor. All right.
Yeah.
But let's say you are just a normal man. You want to go to Laoyat. You want to buy some new CPU for your latest machine, right? So then, generally, if you ask me, I'll just tell people then what you need to know are just certain features of the processor, not so that you know which one suits your use case, right? If you are a gamer, what you want. If you are a graphics artist, what you want, right? Stuff like that. And then I always tell people, buy the cheapest you can get, because no point wasting money on a processor. It's gonna be outdated the moment you buy it. Worse than cars, depreciate faster than cars. So just important things to know about processor. Important features to look at are things like the cache memory. That is a very important feature, which sometimes a lot of people overlook, because that has a very, very great impact on performance. And then of course you look at clock speed, but clock speed, everything also now more or less the same. So it's and caching also more or less the same. So at the end of the day, buy whichever one you want. Right. But if you are a software developer and you are more interested in using the processor, then again it goes down to what level you are looking at. You can be very embedded, like you can use the 8-bit processor or 8-bit microcontroller. And that one you can get for cheap, less than $1 you can get. Or you can even be you'll be more adventurous going to the ARM direction, use 32-bit machines or 64-bit machines. And so it varies what you want to look for depending on what applications you're targeting. Whether you want to, water your plants the machine to automatically water your plants for you, or whether you want to build a machine learning robot. There are many, many features to look at. So it's very hard to give a general recommendation.
Okay. So along a series, you actually cover quite a few processors. Everything is interesting. I'm sorry, but everything is interesting. Yeah.
That's good to know.
Yes. So tell me your favorite. What your favorite that you have covered, and let's start with that first. I'm gonna cover.
Actually, the ones that I've covered are actually all my favorites, but they are all favorites in different categories.
Right.
Like the first processor.
Yeah, go on.
I have different reasons for covering different processors, right? So like for example, first processor I covered was the x86 386, because that was the first processor I ever encountered as a child, right? And then I covered the 68K because that's the first processor I ever designed. Right. And I covered the PIC 16 because that's the processor, the first microcontroller that I ever used. right? And then I covered things like the microblades. I mentioned earlier, I actually designed a clone on the microblades. Then I also I covered the Sun Niagara as well, the T1, right? Because that was a processor that I thought was very cool. Like 20 years ago, you had like 32 threads. It's like Threadripper today you got plenty of threads, but this guy was like 20 years ago, got 32 threads already, right? No big deal, right? And of course, it became better and better after that as well. Then yeah, so I covered different processors. And my latest one, I just covered the Malaysian processor, because very few people know about it, and I happen to know about it. So I thought, okay, let's cover it.
Right.
So all of them are interesting in their own ways.
Yes. Oh man, it just makes it very hard for me to have a follow-through question.
Okay, if you want me to choose, I can choose one.
Yeah.
All right, if you want me to choose, I'll probably choose the Sun Niagara processor.
Okay, but the Spark architecture is not something that we use all the time. I mean, in fact, among our community, I believe the only person that actually uses Michael. He's a big Sun person. So, but even that, I don't know whether he go very deep. But let's talk about that one. That one is interesting because in the 90s, in fact, early 2000, very early 2000, before Sun got crashed down like crazy, the Spark architecture is known to be powerful. The name itself means that it's something to power servers. In the .NET days, when you run servers, you're talking about, as much as possible, you're talking about Sparks and all that. You're not talking about running it on commodity x86 hardware. It's unthinkable. In fact, at that time, x86 is called commodity, and whereas now it's like practice is servers. You know what I mean? So, what can you tell me about the Spark and all that?
Like I mentioned, like I said, I like that particular processor. One of the reasons is because it had 32 threads in hardware. Right, 8 cores, each core can run 4 threads and things like that, so it's 32 threads. Right. But I also like that particular processor because it has one big flaw, one massive flaw. When they, like you correctly stated, when they were designing that processor, they were thinking of using it for the purpose of running servers, particularly web servers. At that time, late 90s, early 2000, .com bubble, stuff like that. Right. So the engineers rightly determined that if you're going to run a web server, you don't really need much floating point operations. What you need is the ability to move data, move bits around fast. So that's integer operations. So they actually designed this processor with completely, very optimized for integer operations, 32 threads, but it had only got one single floating point, one FPU. So the moment you did any floating point operation, traffic jam. All 32 threads can jam at the same point. Right? So as a result, that processor actually didn't do so well initially because of this flaw. They assumed that software developers would not use floating point. But unfortunately, a lot of software developers do. Even until today also, when I meet software developers, I always ask them, why the hell you guys use floating point for? No, you use floating point one. But then there'll be many reasons why they tell me that, okay, they don't use floating point for this floating point. Well, to me, you don't need to.
Yeah, but when we do numbers, we do long, and long is a floating point. Right?
I know long is an integer, but if you're talking about C, right? Long is an integer. If you're doing float, then it's a floating point, right? Then my question is, why do you need to do floating point where everything is digitized, when everything is digital?
Right. I'm primarily a high-level software developer, meaning everything is abstract out. Business application is a floating point, right?
That's where I always show people this problem as well. Okay, I always ask people this question. Okay, if you're going to run let's say you want to write accounting software or banking software, right? What will you use? Floating point or integers? 99 out of 100 will tell me use floating point, don't use integer. And then I will show them what happens when you use floating point. Floating point have natural rounding errors and stuff like that, right? So if you're going to write a banking software with floating point, I'll just show them 1 minus 0.2. I'm banging 1 ringgit, I take a 20 cent, take a 20 cent, take a 20 cent. In the end, not 0, 1. Alright, then I'll say, okay, you imagine you write a piece of code checking to see this account is empty. If the sum equals 0, that if will always fail. It will never be true. Alright, so if you are using floating point for banking software or accounting software, you are doing it wrong. It is supposed to be integers because money is counted. It is not measured. That's why I always tell people. Right. So I don't understand why business software needs to use floating point either. It's integers.
It's an easy abstraction. It's a very easy abstraction to have, because think about it. Literally, all your taxes is by a percentage of your taxes is in a percentage of 100 ringgit. So meaning you need a fraction of one all the time, right? So it's a very easy abstraction to do. But if you're not going to have floating point support, how you going to handle it? I'm going to assume that we don't have software to actually abstract that out yet. But
there is floating point and there's fixed point, man.
Right.
There's floating point and there's fixed point, so just use fixed point. It is a easy substitution, but at least fixed point works using integers. So in that sense, it actually from my perspective, I look at it from a perspective of CPU architecture, right? Then at least it doesn't employ the floating point unit, doesn't use the FPU, it uses back your ALU. So in other words, you can actually benefit from having, like, for example, Sun Niagara would have benefited from 32 ALUs, 32 threads, integer threads running. So
correct me if I'm wrong, but I know that, like, for gaming, for fast computation, people use floating point, but for correct rendering, it's a CPU and it's a integer based kind of calculation.
I don't quite understand the question.
No, what's the thing that we normally use floating point in terms of like
graphics,
let's say graphics and stuff. It is for speed. I mean, by GPU. But I know that it's in industry, like, let's say I'm gonna render a movie, it's gonna be CPU based most of the time. Like ray tracing is gonna be CPU based instead of GPU based, and it's they need the kind of correctness. But it's
I think this thing probably stems from history as well. Like, I don't know for sure, but I'm guessing it stems from history as well, because the GPU is only fast at computing floating point because we made it expert at computing floating point.
Yeah.
We made it optimized to compute floating point. If we had done graphics computations using integers, then the GPUs will actually be integer devices as well. Very, very fast computation done in integers. But we chose to use floating points. Personally, I don't know the actual reason why, because I know for a fact that traditionally, if let's say you're working with OpenGL, you could work with OpenGL either using integers or using floating point. Let's say you want to specify alpha transparency, you could put in either a 1.0 or you could put in an integer 0 to 255. The OpenGL standard allowed for either way. So that means at some point in the past, there was an option, right? But today, basically, it's all floating point already. So you have to use floating point, right? Because the GPU can handle it very well. So never mind. Even though it's slow, but never mind. We got super powerful GPU, it still become fast. Right? And exactly like you said, like, if you want more accuracy, you need integers. Because floating points are inaccurate.
Right. That's a very interesting view. I need to see how they actually implement all these calculations. I do not know for sure because software guys are spoiled. I keep saying that.
Abstractions.
Yes, it's all abstraction nowadays. But literally can't run away nowadays. Data science side floating points somehow, right? I know IBM, they had some special processor to run that kind of thing. The power processor have then their business application. They must have some kind of routine for it.
I'm curious, even because you're the only one that did COBOL. How does COBOL handle money?
It's fixed point. It's fixed point actually. So you literally tell them that run by how many decimal point, decimal n, right, 3, 4, and you literally runs on 3 at most. And it's better tested for, other than that, it's abstracted out. And the only thing why it works so well is that it's been better tested. The power processor have been better tested for so well. The IBM platform is better tested for so well because the only thing they do is taxes, banking, accounting, right? Those guys barely do any text processing. which is why so there is search for record, right? So they literally work on those things are literally things for accountants. So when you want to search for record, literally search for record or do numbers. That's what they do. So as a result, it's pretty well abstracted out. COBOL in a way is the Python of the old days, even though we cringe for saying that, right? Because the main thing they have is that they abstracted out the important thing at that time, at that moment. It's just that their abstraction is high level in the 1950s, and it didn't change since then. We have better abstraction since the 1950s. By 1970s, the abstraction are so different now. The COBOL is considered as I won't say obscure, but yeah, it's considered obscure because nobody remember why they do things that way that time. But the IBM guys, I still try to figure out. I got a feeling that they may be using integer without FPU because FPU is relatively new. If I'm wrong, unless I'm wrong.
FPU standard is actually fairly new. Yes. 1970s.
Yeah,
the FPU.
1970. The IBM guys have their machine running since the 60s, right? So chances is they have some trick there since then that nobody remembers about. So that's the interesting thing. So I remember the
80s,
FPU.
70s.
Yeah, I remember FPU because when I learned. So one thing in Computer Science 101, it's not 101, it's like 102 or something. They have to learn architecture. One of the exercise is to do assembly programming.
I made a mistake. It's 1985. FPU standard 1985.
Yes, that is like only a few years.
So it came up with the 754 standards together.
Yes, IEEE 754.
That's why they have that. So either way, it shocked everyone when you can't do floating point. I kind of cheat. I look at FPU, but I decide against it because I think one thing that we suck at computer science is that we don't go into low level algorithm. How do you do floating point? I'm know for sure that you can do it in assembly and all that, but I don't have proof of that at the time. Now I know it's possible. I didn't implement it at this time. So either way, it's very. I think it's really sad for our education. Oh, so that's a
that way.
Separate topic, sensitive.
Yeah.
Nice.
So do we use FPU nowadays, or is it called GPU now?
Yes, we do use FPUs in a lot of different ways now. And the GPU, like I mentioned just now, is just a very specialized chip with many FPUs inside there, right? But basically, it's FPUs, all floating point, all conforming to IEEE 754 standard.
Okay. You should share the standard. It's really interesting because XKCD actually had a joke about it. It's very funny about floating point. Then they prove it. It's really interesting. So,
well, the joke that we always have about the IEEE 754 standard is that because I mentioned just now there are inherent errors in computation, so your answer is always wrong, but it is consistently wrong. So no matter what processor you have, no matter what OS you have, no matter what language you have, it will always give you the same wrong answer. And that's how you test to see whether you have to do unit testing, right? You test for the wrong answer, you don't test for the right answer.
Okay. I'm thinking about it right now. Any question you can think of, Chilean?
Yeah, like FPU, like it's like GPU is a very specialized processing unit. So what do you see like? Do you have like in mind like what sort of things that can be specialized but gonna be common in the future? Or
Actually, this is a trend that we always see if you look at CPU history, right? The so-called general purpose CPU, there's actually no such thing anymore, because it in a way the processor has evolved according to the times. So traditionally, for example, a CPU was just able to do addition, one thing only. Can only do addition. Cannot do multiplication, cannot do division, cannot do anything else, just addition. But then after that, they find that, oh, okay, people like to do multiplication. Then they add in the multiplier, right? And then as time go on, they notice, oh, some people like to do floating point. All right, so like I mentioned when I talk about my 386, the time that when I talk about my 386 processor, the 386 doesn't have a floating point device built in at all. It's a separate chip. You have to buy it separately and then plug in onto your motherboard, right? So then after that, the 486 came with the floating point built in because they realized that, okay, people need the FPU. And then you move into the 90s, then you find that, oh, okay, actually people don't just need FPU. People want to do multimedia, graphics, audio, a lot more things. So then they pack in more things for like MMX, those are SIMD instructions, stuff like that. They start packing things in. All right, so now as you progress in time, you start to see that, oh, a lot of people now want to do machine learning. Right? Yeah. So machine learning also requires certain kind, not say required, but it can be accelerated by certain hardware. So then they pack things in. So as time goes on, the little so-called general purpose machine it takes on everything. Right? So
you still can run Linux, right?
Yes, you can still run Linux.
General purpose.
Right, it will still run Linux, yes, of course, but it has all those extra features inside there, right?
Right.
And then unless Linux has a driver for it, it won't support it. But if it has, then a lot of things now have even crypto acceleration, right? You have your AES accelerator, you have your SHA accelerators, right? So it moves according to time, not according to what people need. The processor will just keep getting more and more things in there.
Yeah. So I also noticed the trend in a way because as we have this IoT trend going on, I hate that word, I feel guilty. You need SSL. I like it or not, you need SSL because the word, when you want to talk internet, everyone else only know how to talk HTTP, nobody know how to talk MQTT. Even MQTT had encryption, right? So you need, like it or not, you need encryption on board. And suddenly when I read the ESP8266 don't have it, but ESP32 have that. They have a cryptography accelerator. Then I realized that anything that connect to the internet have a accelerator unless your PC or servers, because those things because the algorithm are optimized for those processors for the first place.
I'm curious, do you need a clock for that? Because like SSL requires you to have a
the cryptographic algorithms are not time dependent. Yep. What you're talking about is the certificate.
Yeah.
So you're checking for a certificate, X509 or something. Right. Then that one you need a clock.
Correct.
But the cryptography doesn't need a clock.
But this is how the ESP attack happened, because the clock is not as reliable. So it's an attack against timing. It's not an attack against the cryptographic hardware.
Yeah.
So it's a very different kind of challenge. So what can
that's why you have what you call timing independent algorithms.
Right.
Fixed time algorithms where regardless of what input is given, it takes the same amount of time to process it. That's why it's important to use those algorithms when you're doing crypto.
Right. And it's not as common among...
It completely depends on the library that you pick up. Because there's so many SSL libraries out there. Especially if you're talking about embedded system space. Because we've tried, my company, we've tried Wolf SSL, we've tried Bear SSL, we've tried Polar SSL, we've tried all kinds of SSL. The different kinds, there are a whole bunch of SSL libraries out there, and if you're working in an embedded system, you have to be very picky because sometimes some of these libraries are very big and you've got not enough memory, right? Some of them are designed to be optimized for different things. So if you pick the wrong library and it doesn't have the feature, then you will be susceptible to that attack. Things like that. It's just a matter of picking the right one for you.
So it's basically knowing your constraints, knowing
and if you are talking about IoT, the problem is the hardware is usually very constrained. So like the ESP8266, a little 8-bit processor inside there, it hardly has enough power to do anything at all. Hardly can enough power to do compression, encryption and decryption. Then someone will need to do all these extra constraints thrown in. Wow,
yeah, because when the original design of ESP8266, the protocol is very simple. They just want to send serial over TCP/IP, and that's about it. And it's also very naive. I know it's very naive. They really just want a light bulb to talk to your router, and that's it, right? The thing is,
and they want it to be cheap.
Yes. That's the reason
that's the biggest constraint. Cheap.
Yes, $5 for a $5 for a microcontroller that talk to Wi-Fi. It's amazing, but as a result, it's crazy because I noticed the trend that as a result of ESP8266, all microcontrollers makers are going down price range. They have to match the same price. Uh, the ESP32 is $10. They have to match that price. It's nuts.
Yeah.
It's cool for us that love to build toys, but $10 is amazing. Within 2-3 years, I believe. So, oh yeah,
But
actually,
guess
which
what?
lead to a
The
question.
Raspberry
Yeah.
Pi Zero is $5
Yes.
with a lot more things in it, and I have no idea how
Yes.
people are gonna match that price.
Correct. So, but the one is also the power is a bit horrible. But yes, you're totally correct. Uh, and it's also crazy because you imagine that every Chinese New Year, a kid will get enough uncle to buy a Raspberry Pi Zero. Unthinkable. I mean, yeah, you need to explain and all that, but unthinkable at our time. So,
500
you're surprised by
megabytes
this
of
trend?
RAM.
You're
Sorry?
actually surprised by this price-based trend?
In
Or I mean,
the trend of prices going down is something that's very natural in electronics, right?
yeah,
We all know that, right? The products prices will go down. But what is very surprising to me is the how low the Raspberry Pi actually is. Sometimes I look
yes,
at it and I just look at the cost of the materials alone. The BOM
yeah,
cost alone is already like more than the retail price, and I have no
yeah.
idea how they do it, man. And that's probably the reason why you can't find a clone of it.
Yes,
You see, a lot of other things you can find, like some cheap Chinese clone or something, you know.
yeah,
But the Raspberry
yeah.
Pi, none.
None,
The cloners will probably lose money doing this business. So
yes.
that's probably the reason. I have no idea how they're doing it and staying alive.
I strongly suspect that it's the because it's a foundation, Raspberry Pi Foundation. I know it goes to the politics side, bite me. So it's a foundation. I believe that there's a deal with Broadcom to donate the hardware. As a result, that's the only way I can think of.
Probably like some sort of tax kind of thing for Broadcom, probably.
Yeah, so it's a donation of hardware. As a result, they can put the same set of hardware into industry application. That's where they could charge you heavily, very likely.
And it's also
So
probably a reason why it's always out of stock. Because
yes,
they cannot just simply buy it. It's like dependent on Broadcom, donate to them
yeah,
or whatever. Probably.
right. So I want to go to my second last question I think of because I out of question now. What's the difference between software and hardware in your design point of view? Because you already use VHDL for that, so you already can run on simulator. But do you, as a nowadays, do hardware design is similar to software in a way that you can literally run on simulators or just one piece of hardware like computer you just buy one expensive hardware and can do everything for something we don't even need it nowadays, but I assume that for you guys the cost it'll be similar in doing software in a way that a lot of it is code and you have only few hardware and you can literally do design alone and simulation alone on the chip. Is it true or it is still very different from doing software?
You mean in terms of the process or the
Think of it as a business, like as a business of hardware versus a business of software. Your type of
All right.
business, not the big boys. What's the difference? All
All right, so
yeah,
all right,
go on.
so depending on the type of application, right? Some things are a lot easier to do in software. Some things are a lot easier to do in hardware.
Yeah,
Right. If let's say you go to a traditional software company, then of course they do everything in software, lah. Right. Then because the hardware is their so-called the boundary, right?
Mhm.
So you pick a hardware. It could be embedded system, it could be a server, it could be PC. But once you pick the hardware, then you build the software. You have the whole software stack running on top of it, right? Then if you go to a hardware company, then they will do the hardware, lah. Right. But for people like me, there is actually no clear line between what is hardware and what is software. Because given the problem, I could implement it in the software. The solution, I can implement the solution in software, or I could implement the solution in hardware. Either way also can. So at the end of the day, it will probably come down to cost, which one is cheaper. That's the only question. If like you were talking about just now, trying to run VHDL over simulator and things like that, usually we won't do that lah, because then your performance will not be that great lah, because you're being constrained by the simulator. So if you actually have VHDL or Verilog code written, then we will actually put it into a minimum FPGA long, and then you run it in an FPGA. Because even if you design things properly, even with a slow speed FPGA, let's say running at 100 megahertz, it can easily outperform a multi-gigahertz Intel processor, things like that, depending on what application, what problem you're working on. But it can be done, right? So in that sense, it's down to cost again.
All right.
Anyway, also can.
Okay. Then my final question: power versus power, as in the energy power versus performance. That's the two things happening with the hardware front. Which will you go to? Power saving or more higher performance?
I always believe in power saving.
Right.
Going green. Sometimes I used to actually give a series of talks in some local universities about a topic that I call physical programming, which is basically explaining to them that how they write their software actually can kill the planet or save the planet. Right? Because even simple software operations will, let's say for example, something simple, I always ask them, let's say how do you multiply a number by 2, for example. Right? Some people say, okay, do x equals x times 2 lor. Right, but if you do a multiply, then that will trigger the multiplier circuit, which is actually a very costly circuit. Right? It has a lot of, it's a huge big circuit, it sucks a lot of power. Then some people say x equals x plus x, right? So that will trigger the adder. But then the compiler will compile it and then run the add instruction, right? So, and then the adder circuit will run. It's cheaper than the multiplier, but there's another circuit, you can shift everything to the left by 1. That one is even cheaper because that doesn't even involve any logic gates. It just involves shifting the bits. The wire just go over and that's it. So the amount of current that's consumed will actually be different, right? A multiplier consumes more current, adder less current, a shifter even less current. So how you write your software actually has an effect on it.
But the conundrum is, does it matter if the compiler optimizes it for you?
I always tell people you cannot depend entirely on compiler, because especially when it comes to mathematical operations, the compiler is not always very daring to optimize it for you. Alright, actually you need to massage it. You need to encourage the compiler. This one can compile. This one can optimize. This one can optimize. You actually have to tell the compiler. Then only the compiler should be done for you. And so there are certain things also as a software developer have to do. It's not just leave it to the compiler. Completely let the compiler think about it. Then the compiler won't dare to do it for you.
Right, and that's which limit us to get high power, reasonably power saving code to be written in C, because most of the high level language don't even have that. Yeah,
they don't even care. Right.
So your Python will run into a bytecode.
Well, the way I see it is power is limited, energy is limited. It's a physical quantity that has a limitation to it. Right? Whether we burn fossil fuel or we burn something, there's a certain limit to it. So for the moment, probably we can still say that there's enough computing power to handle whatever the hell we want to handle, right? But in the future, we don't know. Then if there's less and less energy, or energy become more and more costly, or things, happen, we finish our petrol and things like that. Then maybe people will care about, we have to maybe rewrite all this software, or we cannot everything put in a Docker container. Why? Because it's so super bloated with everything inside. But we optimize, strip out, factorize, right?
Yeah.
Maybe go even lower level, and go into the libraries and start tweaking all the little operations. Maybe one day that will come, but today no. Today people are still happy to do whatever.
I think that it's crazy that our Hello World can't even fit a floppy disk anymore.
Yes, there's a lot of blocks.
Yeah. It's amazing. Like it used to be, it's already bad enough that when I start learning C, Hello World is 40 kilobytes. It's still 1% of the floppy disk, right?
And a lot of little microcontrollers don't even have that amount of memory.
No. I mean, sure, your microcontroller just can run a form of Python, but you know how easy it is to crash it. So I have a, let me see if I can bring it out. So this guy here, is so easily crashed. It run MicroPython and everything, those things crash like hell because of memories and all that. Serious. So people underestimate. A lot of people would dream of one day you will run everything a higher language like MicroPython and all that. No, kids, learn your bloody low level language.
I
You don't have a
cringe
choice
every
now.
time. I cringe every time I hear somebody say they want to use JavaScript in an embedded system. Please no, please no.
How about running an
Yes.
operating system on the
Yes.
browser?
Oh, this ESP32 had an operating system. It's crazy. But yeah, even the MicroPython guys is saying that this is a prototyping tool to test your idea. Don't do it in production. Not yet. Not yet. So at least the MicroPython guys is a bit more real. Though it's really insane. I maybe I'll ask your opinion on this. What do you think about high level language on this on the microcontroller class of hardware? Is it a bad idea, or we should just stick with something low level, or we just go with it and all that?
Like I mentioned just now,
Yeah.
okay, there's probably good and bad to it. Because sometimes I'm also asked to go to universities and like judge their final year projects and things like that.
Yeah.
And I've been to universities where I see the students do like, wow, very changgeh one, the project. Like now,
Yeah.
machine learning in thing, right? So I had like one
Yes.
project recently where the student had like a number plate recognition system.
Yeah.
They can, if your number plate is recognized, you open the gate. If not, the gate will
Yeah.
close and things like that. And they built the whole thing, demo it, wow, look very nice. Then I asked them a very simple question. I asked them, what kind of neural network do you use? They have no idea what is a neural network. The answer was, what is a neural network? So there is good
Oh
and
my
bad.
goodness. Yes.
Yeah, so there is good and bad. The good is things are so high level that people can build amazing stuff, but they have no idea what is in it.
I have some things to share about that after we are offline.
So if you ask me, for the general user, it's probably a good thing. But if you're an engineer and you want to make a living in this field, I don't think it's a good thing to work at a high level. You need to actually understand what is in there. So go down to at least an intermediate middle level. No need to go down to assembly, but at least like maybe a C, C++ kind of level is at least better than to just do like super high level language with a ton of libraries for it to help you.
Most of the industry don't agree with me, but C and C++ is a good language to introduce to computing.
I would say C++. C a bit more troublesome, but C++.
Yeah.
C is actually like what we call a dynamic language on a static compiler, something like that.
Yeah. Yes. It's very flexible with void and all that.
No, it's pretty.
C is too flexible.
Yeah, it's too loose. I mean,
too loose.
Yeah, but
so I always tell people, if you want to be a C programmer, you must understand hardware. You understand CPU architecture first. If not, you cannot be a C programmer. You will die.
Yes.
But C++ can.
Yes. Don't do Java. Please don't do Java. Don't do Java as this.
Don't do JavaScript. Unless you're doing
JavaScript.
That's fine.
JavaScript for getting things done, fine. You get things done. It's not a language for fundamentals. I'm sorry, it's not a language for fundamentals. But for concurrency, yes. But concurrency is an advanced topic. Callback, they are awesome at doing callbacks and all that.
You can do that all in C++ now.
Yeah. A lot of the languages.
Modern C++ has all those features now.
Yes.
We have Lambda.
You have modules.
Okay.
We have a lot of stuff now.
I got mixed feeling about Python, seriously.
It's a good middle ground actually, Python. At least if gonna ask, like, at least the type system is saner than JavaScript. Like, you don't have to do the triple equal.
Yes. Yes. So yeah, that's my opinion. And a lot of people don't agree with me. People would use a high level language that would do the work. Come on. Unfortunately, a lot of the kids nowadays don't understand hardware. I'm sorry. Everything on the cloud with serverless, we don't even know how to deploy servers anymore.
Yeah. It's good for business. Yeah. Good for business.
Yes. I just glad that serverless is still expensive. But once it gets cheaper, people don't even know how to deploy servers anymore. Servers, you mean push? God damn it.
Okay,
God.
we have to wrap up now.
Yeah, we have to stop now.
It's
Any
fast, right?
last word?
No, but
I'm good.
And
yeah, we
interestingly,
can do
don't
another
have
one
any
for
question.
more of this. Like
Yes.
one of
Learn
the
C++,
things that
learn CPUs.
Yes. Damn kids. Okay. And we don't actually have question from everyone today.
yeah, we have
Interestingly.
surprisingly more viewers, but we don't have questions today.
Yeah. Did we just scare off people? With that said,
Hope not.
if there's nothing, then we try to get more. So from the team, DevKami team, we will try to get more people to interview next week. If we out of people, we just pull Sean in. But
Oh,
we try to get more people, more variety of people to join us for interview because I know you guys sick of listening to us. So sorry. So that's it. I think say goodbye now. There.
Yeah. Right. Thank you
So we have no
so much for
question.
joining us.
Yes.
bye.
Thanks for listening.